Alright guys, I'm putting up a video with these notes because if I didn't do the video, these notes are really what's in the book. So I really don't want just a book to teach it to you. I think hopefully my voice and explanation can be helpful. So this involves section 10.3 where we're going to have four theorems, but the middle two are very related, so we can kind of combine those. So the first one is the most common one, and that is two minor arcs are congruent if and only if their corresponding chords are congruent. And the if or only if means it can go either way. So if corresponding chords are congruent, then the arcs they create are also congruent. You can go either way in that sense. And in the picture here, basically what I'm saying is if chord AB and chord CD are equal, then the arcs they create, the measure of arc AB and the measure of arc CD, are going to also be equal. And you can keep in mind the arcs will always have to add up to 360 as well, because the circle is 360. So if I add 1, 2, 3, 4, all four arcs up, they add up to 360, but I can conclude that AB equals CD. I cannot conclude AC equals BD. That I cannot. But arc AB and arc CD are equal if these two chords are congruent. So if we look at that with numbers, if arc AB is 80 and arc DC is 80, that means chord DC and AB have to be congruent, or vice versa. If AB is congruent to DC, which is by the numbers, then the measures of the arcs also have to be congruent. And then what an example problem would look like is something like this. If the chords are congruent, we know that arc DC has got to be equal to arc AB. Here, the arcs are congruent, so therefore chord AB is 9, therefore chord DC has to be 9. The next one is where we have two theorems. I just wrote one because one really kind of covers it, but we'll go through the converse so you can see the other one. But it basically says if the diameter of a chord is perpendicular to another chord, so here we have two chords. Okay. Oh, I'm sorry. This should say circle. I apologize. If the diameter of a circle is perpendicular to another chord, and remember, a diameter is a chord, then it bisects the chord and the arc. So anytime we have a diameter, okay, that forms a right angle or is perpendicular to a chord, okay, that means there's a right angle right here. Well, obviously you have a right angle all around here, but it also means that AE and BE are equal, and it means arc AC and arc CB are going to be equal. So in terms of an example, if I have that situation where a diameter is perpendicular to a chord, AF is 6, therefore CF or FC would have to be 6. Arc AB would be 20, then arc BC would also be 20. The last theorem states if two chords are congruent, then the two chords are equidistant from the center point of the circle. The reason why we have right angles here, and we should have a right angle there as well, is anytime I want to measure a distance from a point to a chord, the line that connects that point to the line segment has to hit that line segment at a right angle. Whenever we're dealing with distance from a point to a line segment, we always have to take the shortest possible distance, which always means it forms a right angle. So how would I know if I have a line that has got to be equidistant to the center point? It's based on the fact that I should have a right angle here and a right angle here. And when that happens, we can conclude EF is equal to EG. Your homework is going to be a few problems from your book. Please do the best you can with them, and you will see the answer key on Wednesday. Good luck.